In this lecture, I will discuss the basic concepts of temperature, heat, and heat transfer. Temperature is a measure of how hot or cold an object is. Knowing the temperature of an object gives indication of the amount of heat energy that this object has available to be used to do mechanical work. So as you can see from this definition, temperature and heat are not the same thing. However, the temperature value of an object indicates how much heat energy is available to be used to do mechanical work. Having knowledge of temperature and how to measure it has many applications in today's world. So let's look at a few examples. Knowledge of temperature and the consequences for heat energy availability has applications in heating and cooling, both industrial and household, food preparation and storage, and in technology in general, machining, welding, construction, automotive, and so on and so forth. Temperature is measured with a device that is called a thermometer. Depending on the application, there are several different types of thermometers. We have liquid thermometers, which use the expansion of a working liquid, which would be either alcohol or mercury, to measure temperature. Another type of thermometer is a bimetal strip thermometer. It works based on the different rates of expansion of two metal strips that are glued together. A resistance thermometer is also used. The operation of this thermometer is based on a thermocouple, which the metal from which it's made changes resistance when the temperature changes. There are also infrared thermometers, which use the relationship between temperature and color. And finally, there are also gas thermometers, which use the expansion of gases to measure temperature. To be able to measure the temperature within an understandable standard, a temperature scale must be introduced. The temperature scales in use today are two, and those are the Celsius scale, which is the metric system scale for temperature measurements, and the Fahrenheit scale, which is in the imperial system. Both are based on two characteristic temperature points of the most common substance on Earth, which is water. Both of those scales are based on the freezing point of water, which is 0 degrees Celsius or 32 Fahrenheit, and the boiling point of water, which is 100 degrees Celsius or 212 degrees Fahrenheit. As you can see from the values of the freezing point for each temperature scale and the boiling points for each temperature scale, the two temperature scales, 1 degree on each temperature scale, they're not equal. A degree from the Celsius scale is not the same as a degree from the Fahrenheit scale, which means that in order to convert a temperature from one temperature scale to the other, a conversion formula must be used. And so here, the conversion from Fahrenheit to Celsius is given by this formula. We subtract 32 from the temperature in Fahrenheit degrees, and then we multiply the result by 5 and divide by 9, and this will give us the temperature in Celsius degrees. The opposite conversion from Celsius to Fahrenheit happens by multiplying the Celsius temperature by 9 and dividing by 5, and then adding 32 to the result. Since the Celsius temperature scale has a 0 at the freezing point of water, what is then the lowest possible temperature achievable equal to? The lowest possible temperature that can exist is known as the absolute zero, and that is measured on the Kelvin scale. So what is the absolute zero? Well, if you imagine cube made from, let's say, steel, this cube at room temperature will contain some amount of thermal energy or heat energy, which means that the atoms that make the crystal structure of this steel cube are moving, vibrating about a equilibrium position of their own. As heat is being removed from this cube, the temperature of the cube drops down. And so since heat is a energy that is being removed from the cube, that makes these atoms vibrate less and less. Eventually, so much heat is removed that these atoms can barely vibrate. They're almost stationary. And then at this point, no more heat can be removed, and the temperature of this cube will be the lowest possible temperature that can exist. And this is known as the absolute zero temperature. So theoretically, the absolute zero temperature corresponds to no energy left in an object whatsoever. But in reality, the absolute zero can never be achieved experimentally, so there is always just a tiny amount of heat energy left in an object so that the atoms are never completely stationary. So again, the absolute zero is measured on the Kelvin scale, and this scale is also known as the absolute temperature scale. And this scale is related to this Celsius scale with this formula. If you take the Celsius temperature of an object and you add 273 to that temperature, you're going to get the temperature of this object in Kelvin. There is a absolute temperature scale that is matched with the Fahrenheit scale, and that is known as the Rankine scale. On that scale, the absolute zero corresponds to 400. The absolute zero corresponds to negative 459.67 Fahrenheit. So the relationship between Fahrenheit and Rankine is given again by this formula here. If I have a temperature in Fahrenheit degrees, I would add 460 to that to get the temperature in Rankine degrees. The four temperature scales are presented here in this figure, with the absolute zero indicated for each temperature scale, the freezing point of water indicated for each temperature scale, and the boiling point of water indicated for each temperature scale. Let's do a few examples of temperature conversions. So first, let's convert 29 degrees Celsius to Fahrenheit degrees. The formula that I will use is the temperature in Celsius multiplied by 9 divided by 5 plus 32. So this becomes 9 divided by 5 times 29 plus 32. That is equal to 84.2 degrees Fahrenheit. Notice that here it's important how the order of operation is executed. So first we multiply 29 by 9/5 and then we add 32 to the result. Now let's do a conversion from Fahrenheit to Celsius. Let's convert 314 degrees Fahrenheit to Celsius degrees. The conversion formula for that is that the temperature in Celsius is equal to 5/9, the temperature in Fahrenheit, minus 32. So that is 5/9 multiplied by 314 minus 32, which gives me 5/9 times 282, which is equal to 156.7 degrees Celsius. So here again, we first do the operation in the parentheses, subtract 32 from the Fahrenheit temperature, and then we multiply the result by 5/9. So I discussed all important concepts related to temperature, and now we can move on to talk about heat. Heat is simply a kind of energy that flows from a hotter region in space to a colder region in space. And heat is the amount of energy that is stored in an object, and this energy can flow from or into the object. And so since that energy is contained in the object, it is also known as internal energy. For simplicity, we're going to refer to that as simply heat. The internal energy, or heat, is a combination of the kinetic energy of moving atoms or molecules and the potential energy between the atoms or molecules due to the distances between them. It also has a component that is due to rotations or vibrations of the molecules and atoms. The higher the internal energy or the amount of heat contained in an object, the higher the temperature of this object. Historically, heat was measured in units of calories or kilocalories in the metric system, where 1 calorie is defined as the amount of heat needed to increase the temperature of 1 gram of water by 1 degree Celsius. And the kilocalorie is 1,000 times larger than the calorie, so that is the amount of heat needed to raise the temperature of 1 kilogram of water by 1 degree Celsius. In the imperial system, the equivalent is the British thermal unit, or BTU, and that would be the amount of energy needed to raise the temperature of 1 pound of water by 1 degree Fahrenheit. As it turns out, there is a relationship between the heat that is generated or contained in an object and mechanical work. The relationship between mechanical work and heat was discovered by James Joule. So he performed an experiment in which he had a vessel filled with water. He placed a thermometer to measure the temperature of the water, and then he installed a post to which he attached a set of paddles, and then he tied a string to the post, ran it over a pulley, and when he released the mass to fall towards ground, he found out that the temperature of the water increased. So as the mass is falling towards ground, its kinetic energy increases. Its potential energy decreases, its kinetic energy increases. As a result, that set of paddles here will be, spinning faster and faster and faster. And so James Joule attributed this increase in temperature that he measured to the conversion of that energy that the mass acquires as it falls down towards the ground into heat energy of the water. And so, because of that, heat is measured in joules as well. The relationship between work and heat is expressed through what is known as the mechanical equivalent of heat. So, the mechanical equivalent of heat states that 1 calorie of heat is produced by doing 4.19 joules of work. 1 kilocalorie of heat is produced by doing 4,190 joules of work. And 1 British thermal unit, or BTU, of heat is produced by doing 778 feet-pound of work. The relationship that Joule discovered between work and heat does not go only in one direction, meaning doing work to increase the amount of heat stored in an object is what I discussed on the previous slide. However, the heat energy that an object contains can be used to do mechanical work. And the simplest example would be burning of fuel mixture in the cylinders of a car. So when the mixture explodes, heat is generated. That leads to expansion of the gases, which moves the pistons, and then those pistons do mechanical work. They move mechanical parts, and as a result, the vehicle is moving down the road. Several examples of conversions of heat to work are listed below. The human body, using energy from consumed food, does mechanical work. So the food that is consumed is chemically transformed into internal energy of the body, which then is used to do mechanical work, such as walking, doing things with your hands, and so on and so forth. Steam produced from burning fuels, such as coal, wood, or nuclear, is used to do work on pistons or the blades of a turbine. So what happens is the heat generated by burning of the fuel is used to transform water into steam, and then steam is directed at high pressures at the blades of a turbine. The turbine starts to spin or rotate, and then that generates electricity. I already mentioned in passing that heat flows from a hotter region in space towards colder region in space. And this is the natural direction in which heat flows, from hot to cold. One can never see in nature spontaneous flow from cold to hot. That only can be achieved by doing mechanical work with several different devices, most common of which would be the refrigerator or also the air conditioner. So naturally, heat always flows from hot to cold. There are three mechanisms of the heat flow. That will be conduction, convection, and radiation. Before I discuss those, here is a schematic sort of explanation of heat flow. If I have two objects, A and B, A being hotter than B, and I bring those two objects in contact with each other, heat will flow from the hotter object into the colder object, and that flow will continue until the time where both A and B are at the same temperature. Once they reach the same temperature, heat doesn't flow between the two anymore. The state at which those two objects A and B have the same temperature is known as thermal equilibrium. Now let's briefly discuss the mechanisms of heat transfer. First, we have conduction, which is a result of molecular or atomic collisions, and this type of heat transfer happens when solids or solid bodies are brought into physical contact with each other. Convection is a mechanism of heat transfer within gases and liquids. So this method of heat transfer is common for fluids. Finally, radiation is a method of heat transfer which does not require any medium compared to conduction or convection. A simple example of radiation as a method of heat transfer is the heat energy that the Earth receives from the Sun. In the space between the Earth and the Sun, there is no medium that transfers that heat energy. That heat energy travels in the form of electromagnetic waves. Another example of radiation not needing medium to be an effective mechanism of heat transfer would be a microwave placed in a vacuum chamber. So the microwave oven is placed in the vacuum chamber, the air is evacuated from this chamber, and then you turn it on. It will still work because the microwaves that are used to warm up food can travel through space without the help of a medium. Different substances have different ability to store and retain heat. The heat capacity Q, also known as just amount of heat, is the quantity that tells us how much heat can certain substance absorb. The heat capacity Q is calculated as the product of a coefficient C, which is known as specific heat, the mass of the substance that is being heated, times the change in temperature. Heat capacity for the same mass of different substances varies based on the type of substance. For example, water takes a long time to bring to a boil, but once it is very hot, it remains hot for a long time. In contrast, metals are very easy to heat up, but also lose the heat stored in them very quickly. The heat capacity of water is much higher than that of metals. However, heat capacity is not a good measure of or way to differentiate different materials, because if the mass of the substance is increased for the same change in temperature, the heat capacity must be increased. The heat that is supplied to the substance to heat it up, for that change of temperature to happen, must increase as well. So instead of heat capacity, the specific heat, C, is a convenient quantity to use to characterize substances in terms of heat properties, because the specific heat is the ratio of the heat capacity and the mass times change in temperature. So here now we have normalized the amount of heat necessary to change the temperature of a certain amount of mass of the substance. So now this will always be the same ratio, because if the mass goes up, the heat absorbed must go up. If the mass goes down, the heat absorbed must go down. And so the specific heat is the quantity that tells us whether certain substance can hold a lot of heat or not. Water has a specific heat of 1, and that is one of the highest values of any substance in existence. And so, as we know, water is extremely good at absorbing heat and releasing heat. Water is the working substance that is used in cooling and heating applications. And for example, in the automobile industry, water is used in combination with ethylene glycol for heating and cooling of car engines. The reason that pure water is not used is because of the very narrow range of operation. Water boils at 100 degrees Celsius and freezes at 0 degrees Celsius, and those two temperatures are the temperature of freezing of water is way too high, and boiling temperature is way too low, because engines get extremely hot, or much hotter than that. But adding ethylene glycol to water expands the range of operation of the mixture, which then makes it suitable to use for heating and cooling of engines. Typical units that are used for heat capacity Q are joules or calories or kilocalories in the metric system. And for the specific heat, we have calories per gram degrees Celsius, but other units that can be used would be joules per kilogram Kelvin, joules per kilogram degrees Celsius, kilocalories per kilogram degrees Celsius. So it depends on what the problem statement is and what the units are used in it for the various quantities. These are all possible units for the specific heat. Now let's talk a little bit about expansion due to change in temperature. So first let's talk about expansion of solids. So most solids expand when heated and contract when cooled. And the expansion happens in all three dimensions independently. Expansion of solids is used in a variety of applications, such as thermometers, thermocouples, thermostats. And for example, here we have a bimetal strip made of two different metals or metal strips that are glued together. And so when the temperature of the strip changes, one of the metals will expand or contract more than the other, which causes the strip to bend one way or the other. And so this can be used for thermometers, like this cooking thermometer, where the strip is wrapped around a post which is connected to a gauge needle, and so depending on whether the strip is going to expand or contract, the gauge will move, and one would be able to read the temperature that the thermometer measures. Another application of a bimetal strip device is a circuit breaker for an electrical circuit. once the temperature here increases enough, this strip is going to disconnect the circuit, and when the temperature drops, the strip will close the circuit. So the formula that describes the change in length due to temperature change is shown here, where delta L is the change in length, alpha is the coefficient of linear expansion, L is the original length of the solid, and delta T is the change in temperature. So let's consider a metal rod which has length L and is at temperature T. So if I heat that rod, what will happen is the temperature will increase by the amount delta L. The length will increase by the amount delta L, and the temperature will change by delta T. So then I can write the relationship between the initial length and the change in length as the formula that I showed on the previous slide. So the change in length is equal to this coefficient alpha, which is the coefficient of linear expansion, times the original length times the change in temperature. Coefficient alpha the coefficient of linear expansion is measured in units of 1 over degrees Celsius or 1 over degrees Fahrenheit. Materials can also expand in 3 dimensions at the same time by volume. So solids do that, and also liquids. Gases do not behave the same way as liquids and solids in terms of volume expansion. So this discussion only pertains to solids and liquids. So when a liquid is heated up or cooled down, it's going to either increase its volume or decrease its volume. And this process is happening in 3 dimensions at all times. And so the relationship between the change in volume and the original volume is given by the formula here, where delta V is the change in volume, beta is the coefficient of volume expansion, and V is the original volume, and delta T is the change in temperature. This formula applies for solids as well, where the change in volume here will be the product of change in length of each dimension of a solid, and the coefficient beta is equal to 3 times the coefficient of linear expansion alpha. So that's the relationship. The units in which beta is calculated are also 1 divided by degree Celsius or 1 divided by degree Fahrenheit. Let's look at the following example of calculation of using the concept of change of volume expansion. So a car radiator is made from copper, which has coefficient of volume expansion of 51 times 10 to the negative 6 per degree Celsius. The coolant has a coefficient of volume expansion 4.1 times 10 to the negative 4 per degree Celsius. So if the radiator is filled to capacity, which is 15 quarts at 6 degrees Celsius, how much coolant will spill into the overflow reservoir when the temperature reaches 92 degrees Celsius? So to solve this problem, I'm going to calculate the change in volume for the radiator and then for the coolant. And then I'll take the difference, and that's going to give me the amount of coolant that's going to spill into the overflow reservoir. First, I calculate the change in temperature, delta T, that's 92 degrees Celsius minus 6 degrees Celsius, that is 86 degrees Celsius. So for the coolant, the change in volume will be equal to the product of the coefficient of volume expansion, the volume of the coolant, change in temperature. So that's 4.1 times 10 to the negative 4 per degree Celsius times 15 quarts times 86 degrees Celsius. So the change in volume of the coolant is 0.53 quarts. For the radiator, the change in volume of the radiator is equal to the coefficient of volume expansion for copper times the volume of the radiator times the change in temperature. So that's 51 times 10 to the negative 6 per degree Celsius times 15 quarts times 86 degrees Celsius. So the change in volume for the radiator is 0.066 quarts. So as you can see, the coolant expands more than the radiator. So some of that will spill into the overflow reservoir. So how much is that? That will be 0.53 minus 0.066 or 0.46 quarts. So that's how much coolant will spill into the overflow reservoir. And so this concludes the lecture on temperature, heat, and heat transfer.